Hi, in this video we're going to study a fundamental problem in computational geometry. The problem is the closest pair of points. The input to this problem is a set P of n points in the plane, as I've drawn here. And the output are 2 points, x1 and x2, that have the shortest distance from each other. For example, here, the 2 points would be this one. You can always solve this problem via a trivial algorithm which simply computes every distance among every pair of points. There are n points, so if you compute this, it will take at least time n squared. Next, we are going to see a clever algorithm which has a much better running time of just the order of n log n. For this algorithm, we are going to assume that we have two arrays, x and y, each containing all the points in P, and moreover, x is sorted with increasing x coordinate, so this way. So for example, x could list the points in this way, first this, then this, then this, then this, then this, then this, then this, this, and so on. And y is sorted with increasing y coordinate. So y would list the points in this order. This. The algorithm is a great example of divide and conquer. Let's see it. The first step is to divide. The divide step here is fairly natural. We are simply going to divide the points in half. We are going to pick a vertical line L, which cuts the points in two sets. PL, the points which are to the left of L, and PR, the points which are to the right of L. And PL and PR should have roughly the same size. So they should be n over 2 plus or minus 1 if n is odd. The conquer step is also fairly natural. We are going to recursively call the algorithm on each side. Okay. We're going to make two recursive calls to find the closest pair in PL and PR. So in PL, it would be this pair here, which has a distance delta L. In PR would be this pair here, which has a distance delta R. And then, since we are interested in the minimum distance overall, we are going to let delta be in the minimum of delta L and delta R. So here delta would be equal to delta L. Okay, now we have to combine these two partial solutions into an overall solution. And this step is the more clever one. We observe that the closest pair overall is either the one with distance delta, so it would be this one here, or of course it could be a pair which has 1 point in PL and 1 point in PR, so a pair which crosses the line L. So this seems problematic. It seems that we are back to square one. We have to try every point on the left with every point on the right, and this would again be a quadratic time algorithm. However, the fundamental insight is that when you look for such pairs, you don't have to look for any possible pair, but you only have to look for pairs which lie in a delta cross 2 delta box straddling L. So a box like this. Okay. Why is this? Well, because if the closest pair involves a point which is farther away from L than delta, then clearly cannot be part of a solution because we already have a pair which has distance delta. Okay. That's why you only have to look for pairs in this delta cross 2 delta box. The other ones cannot contribute to a solution because just to cross the line L, you will have distance at least delta, and again, we already have a pair of distance delta. So now the question is, how are you going to find such pairs? And there is a clever way of doing that, using the arrays x and y, which we constructed before. Here is how you can find the points in the box. Okay, as we mentioned earlier, we have the array y, which lists all the points in increasing order of y coordinate. Okay, so now from y, I'm going to create another array, y prime, which is obtained from y by removing all the points which are not in a vertical strip of length 2 delta. Okay, specifically, here is the strip. Okay, so this distance here is delta. And I'm going to throw away all the points which are outside of this. When I do that, my new set of points looks like this. Now I have only points whose x coordinate is a distance at most delta from L. Once I have this, I'm going to do the following thing. I'm going to go through all the points in y prime, and for each consecutive 8 points, p1, p2, p8, I'm going to compute all their distances, and if any of them is closer than delta, then of course I'm going to update the closest pair and the shortest distance delta. Once I'm done, I'm going to return delta and the closest pair. Okay, so you're going to go through y prime in order, starting from the top point. Start from this. Then you look at the next 7. So with this it would be 8. There is some points here. You compute all their distances. Okay, and if you find something which is closer than delta, you update the shortest distance. Otherwise, you move to the next point. Again, from this, you look at the next 7. You compute all their distances. If you find something which deserves an update, you update. Otherwise, you move to the next point, look at the next 7, compute all their distances, and so on. This is the end of the description of the algorithm. And now we just need to ask ourselves, why does this thing work? Why suffices for me to look at the next 8 points, at the blocks of consecutive 8 points in y prime? Okay, and the reason is this. Remember that we are looking for points which are in a delta by 2 delta box. Okay? Okay, so once I get my first point, like this, okay? In my algorithm, I'm just going to look at the next 8 points, the next 7 points, so that with this it would be 8 total. Okay. And that's because I'm claiming that if you go further than that, the point will not be in the same box as my first point. And why is that? Because if you happen to have 9 points in a delta by 2 delta box, okay, since you have 9, there's 2 squares here. One of the square must have at least 5 points. Okay, of these 9, at least 5 must lie in the same square. And if you have 5 points in a delta by delta square, then you can verify that you have at least 2 points which are a distance less than delta. Okay, I'm claiming that if you place any way you want 5 points in a delta by delta square, then at least 2 points have distance less than delta. And this violates the definition of delta. if we want to verify this implication here, that if you have 5 points in a delta by delta square, you have at least 2 which are closer than delta, we can think of subdividing each square further in 4 little squares. And now we see that any way in which you put 5 points, you will have necessarily 2 points in the same subsquare. And if you have 2 points in the same subsquare, they will have distance less than delta. What remains to analyze in this algorithm is its running time. And the running time is the same as merge sort. Okay, if T of n is the number of operations on n points, we have recursion T of n is equal to twice Tn over 2 plus Cn, which resolves to order of n log n. That's it for now, and I will see you later.